Hey everyone, Morgan here. Welcome back to your Honors Chem lectures. We're going to start off this semester by looking at periodicity and the periodic table. So periodicity can basically be referred to as repeating patterns on the periodic table itself. Okay? And that's going to be pretty much the theme for the whole chapter. All right. Our first periodic table was brought to us by the Greeks, so 3,000 years ago. Okay, 4 elements. None of them are elements, but at the time it was a pretty good guess. Earth, air, fire, water. Okay, solids, gases, liquids, plasmas. Okay, they're not elements, but it was a pretty good idea. Okay, now the periodic tables that we're using today really were born with Dmitry Mendeleev, a Russian, who lived from 1834 to 1907. And he was the last of 17 kids in his family. Okay, he took note cards, put the names of the elements on them, and laid them out on the table in front of him, and started rearranging them over and over again until he found what he thought made sense. Mostly it was based on atomic weights, which we don't do anymore, okay, because he didn't know what the atomic number was, okay. Protons had not been discovered at this point, because this was, I'm going to say, sometime in the 1870s that he started to work on this. Now, when he arranged out all his note cards, what he discovered was that there were holes in his table. There were places where there should have been elements and there weren't. And he didn't call it a mistake. He just said, I'll bet we haven't discovered these elements yet. Okay, and he was correct. All right. Now, Mendeleev himself was never awarded a Nobel Prize. The prizes first started to be given out in 1901. So he was alive during the time period when they were being given. But there was a lot of negative feelings on the part of the Nobel Board towards Russia in general. Okay, and this is back in the point where it was Russia. It hadn't become the Soviet Union yet. Okay. And they were very centered on scientists in Central Europe. Okay, so had he lived longer, he probably would have ended up with a Nobel. Okay, one of the elements that he figured was missing, he called eka-silicon. He said it would have been just beneath silicon in his periodic table. So on periodic tables now, that's the element germanium. He predicted the properties of this element. He thought its molar mass would be 72 AMU. He thought it would have a density of 5.5 grams per centimeter cubed, or grams per milliliter, you can say it either way. A specific heat of 0.31, that's in joules per mole Kelvin. Okay. He thought that the melting point would be high. Actually, he said very high. He didn't assign a number to it. He thought the oxide would be something with 2 oxygens on it, and that the density of the oxide would be 4.7 grams per centimeter cubed. Okay? Now, it turns out, once discovered, the molar mass was 72.3 AMU. 5.47 grams per centimeter cubed for the density, 0.32 joules per mole K. The melting point was 960 degrees Celsius. I think we will all agree that that is a pretty high melting point. The oxide formula, he was correct. It's GeO2. and 4.70 grams per centimeter cubed for the density of the oxide itself. Okay? So he was pretty spot on with this. Let's accept that. All right? So his ideas of periodicity were really good ideas. Okay, so now the table that's in front of you came into existence, so to speak, in 1947 officially. There was a guy named Glenn Seaborg. He was born in Ishpeming, Michigan, which is a very small fishing village that none of you would be familiar with. Okay? I've got family in Michigan, and they don't even know where Ishpeming is. It's so small. His family moved to Southgate, California, mostly because of the Farmer John meatpacking plant. There were good blue-collar jobs to be found. So Seaborg is a graduate of the LA Unified School District. Then went on to UCLA, studied chem, went up to UC Berkeley, okay, got his PhD and never really left, became full professor, president of the university, all that. Now, while he was working on the Manhattan Project in World War II, he came up with an idea for a new table structure. But he couldn't publish it until 1947 because of security reasons. It was just that he was under government contract at that point and wasn't allowed to publish. Now, what he said was, let's give up on organizing by atomic mass, and let's switch and let's do it, number one, by atomic number, and number two, by electron configuration. So atomic number and electron configuration. And we're going to have some videos about electron configuration up for the weekend. So that's where it looks like this. His real big idea was to take this part and pull it out from the table as it normally appears. Okay? And it's still around today. So, groups on this table are the vertical columns. And periods are horizontal. And there are 1, 2, 3, 4, 5, 6, 7 periods. Remember, these two actually fit right into here. Okay? Now, on this table, the way it turns out, this was not his design, this was just how it turned out. Over here we have the metals on the left side, and over here we have the non-metals. Now, there are a few elements on this zigzag line that we've got here. Silicon, germanium, arsenic, antimony, and tellurium that we call semi-metals. Or some people like to call them metalloids. Okay? Not everything that touches that line, but officially those 5. Okay? Now, we're going to take some time here and talk about how the elements appear as metals or how the non-metals appear. So we need some words to be able to do that. So, luster, whether something is shiny or not. Okay, S-H-I-N-N-Y? No, S-H-I-N-E-Y, probably, okay? Or instead of shiny, we might say colorful or bright. Okay. Now, malleability is the ability to beat and shape. Ductility is the ability to stretch it out into a wire. Okay? And conduction is whether it can carry. We have heat conduction, something that carries heat. We have electrical conduction, something that can carry an electric current. Okay? Now, let's go on the next page. And let's compare metals and nonmetals and those properties. Metals. Okay, they appear gray or silver, and they have a lot of shine to them. Okay, at least when they're polished up. Non-metals, they look brittle. Mostly, it's a lot of gases that are non-metals, so there's no appearance. Okay, they're not shiny. Okay, now semi-metals look like metals. Metals are very malleable. We can shape them. We've been shaping metals for 1,000 years. Okay, but non-metals tend to be brittle. If you hit them with a hammer, they're going to smash. And I'm really missing a lab that we do in the classroom where you literally take a hammer and beat on some metals and some non-metals to see that happen. Now, semi-metals are also brittle. So sometimes they'll have the properties of metals, sometimes they'll have the properties of non-metals. Metals can be stretched into wire. They are ductile. But because non-metals are brittle, if you try to stretch them out, they just shatter. Okay? Semi-metals, no. Luster, metals have it once they've been polished. Non-metals, no. Okay? Semi-metals do have that luster. Metals are good conductors of both heat and electricity. Non-metals are what we call insulators. They are not conductors. Okay? Semi-metals are poor heat conductors, and they're okay, maybe to good electrical conductors. At 25 degrees, metals are solids. One exception, mercury is a liquid. Okay? Non-metals, it's mixed. We've got all three phases. We've got solids, we've got liquid, we've got gases. Okay? The semi-metals are solids. Melting points are very high for metals. They're very low for non-metals. And it's a bit mixed here also. Okay? Oh no, I'm sorry. I'm messing that up. No, actually very high for semi-metals. Metals tend to form positive ions. Non-metals tend to form negative ions. Okay? And you get both for semi-metals. Now later on we're going to be talking about these two things. So we'll just, for now, we'll say that metals have low ionization energies and electronegativities and high for non-metals and kind of in the middle for the semi-metals. Okay, so that's your first lecture for this unit. We'll be continuing on with the rest of the outline in some further videos. This is Morgan, signing off.